the good thing about going at this part of the presentation is that many people have already talked about a lot of these subjects that I'm going to bring up here, which is great. So you guys already have a background in it. But as we know, and it's been mentioned many times, a lot of the lowland streams in Whatcom County do not meet their minimum in-stream flows for many times of the year, specifically kind of in the summer and late fall. And this creates low water levels and poor water quality. And as Treva in her presentation brought up, there's some significant problems with that when it comes to fish habitat. And I wanted to point out to Becky, who made a comment in her instructions to me about making slides that showed something, you know, low water level, fish out of the water. Trying to follow your instructions. So the solutions we kind of came up with, one of them would be to transfer surface water rights that are directly on the stream, off the stream, and into water wells located a certain distance away from the stream, and basically taking groundwater at that point. The other one would be to just take wells that are located a certain distance away from the stream, pump water directly out of the wells into the stream during those times of the year when we think the streams need it the most. And the result of that would be, you know, more water quantity and higher water levels in the stream, and hopefully an improvement in water quality. Examples of a couple projects that we've been doing here are in the Bertrand Creek Basin, working with the Bertrand Creek Watershed Improvement District out there. Since about 2010, the WID has been encouraging farmers to transfer water off of the stream and put it onto groundwater wells. And I wanted to show here, see if I can do this without losing this, but this is just a chart showing flows in the stream during the summer in 4 years, 2003, 2006, 15, and 16. And most of you probably can remember that 2015 and 16 were fairly droughty years. Sorry. Well, 2003 and 2006 were also pretty droughty in the summertime. And again, you can look, these are the 3 months precipitation totals during the summer months. They're about the same. Well, back in 2003 and 2006, in the months of July and August, we had flows in Bertrand Creek at the Rathbone gauge that ranged from maybe a high of 5 CFS to a low of maybe 1.5 CFS. Now, back in 2015, 2016, under similar climatic conditions, we had flows that were on the low end of about 5.5 CFS and up almost near 10 CFS. And so we think that the fact that we're transferring a lot of this water off of the stream is making a significant difference to stream flow. Another project that the Bertrand WID's been working on is, again, a direct stream flow augmentation using wells that are located near the stream. In this case, we were using in the fall of 2017 infrastructure and wells that were owned by Mayberry Farms. And the idea here was we want to take groundwater out of the Sumas aquifer in this case, pump it directly into the stream, and the impact from that groundwater withdrawal hopefully would show up in the stream at a later time, a much later time. So maybe in November, December, if ever. And therefore, that's back when the stream is actually meeting in-stream flows and there's a lot of flow in the stream. So we started a pilot project on this on, I think it was September 13th. We started pumping in about 1.1 CFS into the stream, 3 or 4 miles above upstream from the Rathbone gauge. After about a dozen hours or so, we started to see an impact on the Rathbone gauge, and within about 20 hours, we saw 1.1 CFS, additional water in the stream. We ran that project for, hit the wrong thing. Ran that project for about 4 to 5 weeks during the fall. It was hard to follow the water, the whole 1.1 CFS, to make sure that it stayed in the stream because of some issues with, there were some continued withdrawals from the stream that were authorized or unauthorized, I really don't know. But also there was rainfall events in there which created some problems with the hydrograph. And in fact, at the end of about 4.5 weeks, we had a significant rainstorm, and we barely got our discharge structures out of the creek before they got washed away. So we were able to save them. So I want to talk a little bit about the challenges associated with some of these things. Surface water to groundwater transfers. you have to find a property owner, a water right owner that's willing to do this. And there's a lot of reasons for them not to do it. One, they basically need to take their water right and go through the change process with ecology. That means opening up their water right to ecology. They have to pay ecology to process the water right, which is an expense. And then also, if they don't have a well or something that they can transfer this to, they may have to actually drill a well, put a pump in, do all of those things. So it could be very expensive for them. You have to have the right geology and hydrogeology. If you have a water right off the creek that, say, it's 1 CFS, that's about 450 GPM, and the aquifer that you have nearby that you want to use is not really of a high permeability, and maybe you can put a well in there that does 75 GPM or maybe even 100 GPM, you're going to need a lot of wells to get your 450 GPM, and that may be a big problem. Groundwater quality can be a problem. These are generally irrigators who are using this, and going to groundwater in many parts of Whatcom County, the groundwater could be high in iron or some other contaminant that creates a problem with their distribution system and their irrigation system. So it's, again, an additional maintenance problem. There's been a number of people have brought up the Foster decision. The Foster decision is a real problem with these kind of transfers because I think Mark mentioned before, it basically says you have to do things that have to be in kind, in place, and in time. Irrigation water rights are for a set time period usually. Let's just say June 1st to September 30th. And if you're pumping out of a river and you have the right or the stream to pull water from June 1st to September 30th, then you transfer it to a well that's a certain distance away, the impact from that well may not actually hit the stream for 2 or 3 weeks or even longer. So therefore, now you no longer have the ability to pump out of your well all the way to the end of your irrigation season. You may have to say, okay, I'm going to voluntarily not pump water out of my well, say on September 1st rather than September 30th, so that I'm not impacting the stream beyond the time period when I had legal right to under a surface water right. That limits, again, the farmer. So it's another impediment in trying to get people to do these kinds of transfers. Streamflow Augmentation has its own set of challenges too. Again, you have to have a proper geology, hydrogeology. Again, the concept here is to take groundwater out of storage out of the aquifer and pump it into the stream. Well, we want to put quite a bit of water into the stream, and you need to have aquifer that's permeable enough and can produce enough water in certain areas so that you can get that water into the stream. Groundwater quality can be a problem on that end. If you've got a groundwater compatibility problem with what's in the aquifer and what's in the what's actually in the stream, there may be an issue there that you have to work through. A lot of regulatory issues associated with this. If in the WIDS case, they actually went to ecology and they got a temporary permit from ecology to divert this water, to basically pump it out of the ground and put it into the river. That's a long process, expensive process to go through. The other way to do this would maybe be able to identify a groundwater right that you could go through the change process and maybe change to do this. But again, that's another long process and it's expensive process. So where can these types of methodologies be applied in Whatcom County? Generally, the geology and hydrogeology is pretty favorable in the Bertrand Fish Trap, Johnson, and Cam drainages. And it seems like there's probably a good possibility of being able to do these things and get them to work. Dakota, California Creek basins, possibly there too, but the surficial aquifer there is quite a bit finer grained and doesn't really have the ability to produce as much water. But there is a deep aquifer at depth below those that does have pretty good water quality, and it's maybe possible to utilize that. And there may be other areas. There was some mention of the Sumas drainage. The Sumas may have some areas up there that this could be utilized on. It's kind of got a unique geologic kind of setting. May require a little bit of different approach, but it could be done. And I finished early.
Thank you, Chuck. Our next speaker for the afternoon is Dan Isis. He's with Birch Bay Water and Sewer District. He's been there for, I think 13 years, most recently since about 2015 as the actual manager, and he's going to talk about a deep water aquifer project.
Jay earlier today had the cross sections of some of the three main aquifers in the county: the shallow, there's an intermediate, and the deep aquifer. This discussion is on the deep aquifer and in the Blaine area. I pulled a report off the shelf this morning, the Blaine Area Regional Water Supply Study. It was from January of 1976. So this concept and project has been around for a while. The 76 report was actually looking at Blaine supplying Birch Bay as a regional water supply. At this point, we're getting a little bit bigger and looking at whether the deep aquifer is large enough to supply more than Birch Bay and Blaine. A little background on the Birch Bay Blaine system. Blaine owns the wells. The rectangular area up there is the well field. They own 13 wells. Majority of them are in that well field. They supply water to Birch Bay and to Bell Bay Jackson. The blue outline is the City of Blaine groundwater management area. This was a designation that was recognized by Department of Ecology in the 90s to help protect this groundwater area. The Dakota, in this outline, is basically the Dakota Basin. At this point, the Dakota Basin is closed to further appropriations upstream of the tidally influenced area, and that dot is what we say the tidally influenced area is. So you can see that there is areas downstream from that tidally influenced that is open to further appropriations per the in-stream flow rules. We used that and worked with ecology to get new groundwater rights in 2010 for this area. The deep aquifer is, we have information on it from Blaine. We've had a couple of wells drilled in the Linden area that did run into the deep aquifer. In that area, it had poor water quality. And in between those two areas, we didn't have really any data that said where's the extent of the good water quality versus the poor water quality. About 2 years ago, the district received $700,000 from Department of Ecology to help assist with determining what is the extent of this deep aquifer and what is the long-term sustainable yield. With those dollars, we've drilled three deep wells, EW1, and this is out on the Delta Line Road. There's EW2 and then EW3, which is over on Giles Road. So we kind of spread them out to try and get a good cross-section of information. The first well we drilled was about 440 feet deep, and we actually did hit bedrock in that location. That one actually had low water quality and low water quantity, low permeability. Wells 2 and 3 went 423 feet deep, and number 3 went 600 feet deep. Both of those wells had good water quality and quantity. For the geeks out there, these are the cross sections of 2 of the wells. Chuck likes to produce these when we get done drilling. They have similarities in that the first 300 to 350 feet is glacial marine drift, is what Chuck calls it. I call it clay. I like clay. In this instance, it gives us good separation between the deep aquifer and the shallow aquifer, and interferences or connections with the surface waters. Thank you. That was the wrong that was the wrong button, though, wasn't it? Okay, I'll try not to do that again. Here's a drawdown test that we did on the second well. Basically what this shows, we pumped at 650 gallons per minute for 72 hours. We only had 35 feet of, I wasn't pushing any buttons. We only had 35 feet of drawdown. That's excellent results. The third well had very similar results to this, and it had about 70 feet of drawdown. Both of those examples are actually significantly better than what we currently have in the well field that Blaine has been using for years. So the results from those two wells were very good. The production was actually limited by the size of the casing. How big of a pump could we put into the casing versus how much water was actually there. I did it again. Let's see. One of the things was trying to get the extents of this aquifer. Where is the poor water quality between Blaine and Linden? Where is it located? We have a theory that it is related to the bedrock elevations that's actually down there. This is our best guess at bedrock elevations. It's difficult to see from up there, but basically we think that the Linden area is in a bathtub of bedrock. So when the poor water quality gets in there from the glacier time period or before, it basically stays there, versus being outside of the bathtub area, the water has been getting flushed out and has gotten good water quality over time. So trying to find out where is that dividing line of where we can get good water versus the poor water quality. This EW1 that I said was a poor water quality and poor quantity, it actually, from an information point, was very good. We think that's got to be very close to that dividing line. The thought being anything to the east of that area would get into the poor water quality. Towards the west, our theory is that it would be the good water quality. We've thrown some stars on here as far as other places to drill in the future that we think could produce the good water quality and quantity. One caveat on that dashed line between what we think is the poor water quality and the good is that's based on just a couple of data points. When you're going 400 or 500 feet deep, it's expensive to get the data points. But it's our best guess at this point. And then the last thing that we're doing with this ecology grant is doing a short feasibility study, basically calling it a phase 1. And it's looking at where could this water be used? What would it take to send it east towards Linden area to take care of some of the nitrate problems in that area? What would it take to send it south and southeast towards Ferndale area, and if you did that, what kind of problems could you help solve? The feasibility study is currently almost drafted, right, Chuck? It's supposed to be done shortly. I would expect it to be out in the next month. It will not provide answers for where we think the water to go. It will provide options of what you could do with the water, and it would be getting the discussions going of what is the best use. And we are hoping for additional funds to continue the exploration and continue on with the feasibility as we get some of those discussions moving. Early also.
Thank you, Dan. Our next speaker is Sarah Ciarabi. It looks like there's a lot of vowels in there. Okay. Sarah's going to talk to us about rainwater catchment, and this is rainwater catchment into cisterns, larger storage units as possible water supply options. I will tell you that We did, as part of our speaker series, a half-day forum out on Lummi Island last summer in June. This was one of the topics that came up. We got a lot of suggestions for them. They were very interested in this. They wanted to have people come back. So this summer in August, we're going to be working with them again to put on probably another half-day event focused exclusively on rainwater catchment. So you might keep your eyes open for news about that if you listen to this and think it has some interest to you or people that you know. Thanks, Sarah.
I hope you can hear me. Last night, my 12-year-old boy is officially taller than me, so that's fun. My name is Sarah. I work for the Whatcom County Health Department. I have two jobs there. One part of my job is I work in the operation and maintenance program, which means I inspect septic systems. The other part of my job is I work as the health department liaison for the planning department, where I review building permits and development permits for drinking water requirements and sewage requirements, and I also answer a lot of questions about the Hearst decision. Many questions. So today I was asked to talk about water conservation, and at the health department, where we get involved in that, like Sue said, is rainwater catchment. So I'll be talking about that and a little bit about gray water systems and just one slide on low flow fixtures. So rainwater catchment. So this slide is really about what rainwater catchment looked like before October 2016. In 2009, the Department of Ecology came out with a policy that said rainwater is no longer considered waters of the state, and property owners can capture it and use it. So what that meant for the health department is that if you had a piece of property that you wanted to develop, and there was no public water available and the wells were dry, that you could use rainwater catchment as your potable source. So from 2010 to October 2016, the health department approved 13 rainwater catchment systems. And as you can see, from October 2016 to present, we've approved 14, so the same amount as we did in the last 6 years. And that was directly related to the Hearst decision. That became a viable option for people to develop their property when they couldn't use their well. So it's a two-step process. You get somebody to design your system, and that gets you building permit approval. And then once you install it, you have your affidavit, or you have your installer sign something that says, yep, we put it in according to design. And that'll get you final occupancy. You can actually live in the house that you built. At the health department, we only track rainwater catchment systems as it relates to development. So if somebody put in rainwater catchment after the fact, so either their well went dry or they wanted to supplement their drinking water, we will be happy to advise them, but we don't keep track of that information. So how do we determine how much rainwater you might need to harvest and store to get you through a year? The information that you need is how many people are going to be in the house and where are you in the county. So in this example, I'm using 2 full-time residents, and there is a provision if it's a vacation home, then that's a different equation. In this particular example, you're in Bellingham, so you get about 35 inches of rain per year. You run that through the calculation, and you need a roof size of 16,739 square feet. That's how big it has to be to capture rain for the year. And then also the storage size is 9,000 gallons. That's the minimum. We would definitely recommend more if you wanted to do irrigation outside or just to have a buffer. And I would imagine most people would probably just buy a 10,000 gallon tank. It's probably more readily available. So for in Lake Whatcom, if you have the same situation, your square footage for your roof goes down because they get more rainwater. So you can see at the bottom there that Lake Whatcom gets 64 square inches. So we do account for that in the equation. It does need to be designed by either a professional engineer or somebody who's associated with the American Rainwater Catchment System Association. You can't just have any old roof on your house if you're going to use this. We want you to have an enamel tile or cement tile. And also everything has to go through filtration and disinfection. So you can't bypass the system to flush your toilets. We want the whole system to be treated. Also, the property owner has to have an operation and maintenance plan. So this puts forth what's expected of them to maintain the system. So how often you're going to clean your roof, your gutters, how often you're going to change clean your storage tank, and also how often you should test your water. And this document is signed, notarized, and recorded against the property, so future property owners also know what's expected of them. I've heard anywhere from $10,000 to $25,000 for cost for a rainwater catchment. So the next thing I'm going to touch on briefly is just gray water. Gray water makes up about, you produce about 40 gallons per person per day for gray water. And this chart I got from the Water Research Foundation, and I highlighted the yellow areas that those fixtures that produce gray water. And their numbers, they came up with about 80 gallons per house per day, which is about, of course, 40 gallons per person per day. So gray water is not inert. It's definitely something that can pose a risk to public health if it's not treated well and if it's not handled carefully. So you have to be careful what you're putting in your system, because obviously whatever you put in, you're going to get out. In 2011, the Department of Health set forth requirements for using gray water for subsurface irrigation. Local health jurisdictions had 3 years to implement this unless resources prevented otherwise. And here in Whatcom County, we do not implement this gray water regulation. The intention behind it was to encourage water conservation, but also by protecting public health. Like I said before, gray water is not inert. You can't just discharge it to the ground because it could cause harm. So you still need sewage system, or you need, so you either need a septic system or a sewer to divert your gray water to when it's not the growing season. And since this is for subsurface irrigation, the plants aren't going to need irrigation all year round. So you need a way to divert that gray water when they don't need it. Reclaimed water, so water that you might use to flush your toilets, is actually handled through the Washington State Plumbing Code, which I didn't know that. That was interesting to me. 2 ways to conserve water. You obviously reduce the water coming in, and we want you to reduce that causes the amount of water to go out to be low as well. And in Whatcom County, you can do that with a waterless toilet and a gray water system. So a waterless toilet would be like a composting toilet or an incinerating toilet. And it doesn't get you out of the need for a drain field, but it may reduce the size because you're not putting as much water into it. I was talking to a coworker who's been with the health department for 20 years, and he has only approved 2 of these systems, and one of them is no longer in use. And I think the reason why is that people, once they realize they still need to have a drain field, they're like, well, I'll just put the whole thing in. So like Whatcom County doesn't follow or decided not to implement the Department of Health code, and so we use our own code, and then we have a list of registered products that people can pick from that tells you exactly which composting or incinerating toilet you can use. So just one slide on low flow fixtures. This is actually done through building services. The energy code requires a certain number of energy credits for new construction. And energy credits can be acquired during through multiple systems. So you can either do it through an efficient furnace or increasing your insulation, or you can also do it through plumbing. So people have a choice. So if you really want a robust shower, you might make up your energy credits through insulation. So if you want a credit for low flow fixtures, you can see there you need 1.7 gallons per minute or less for your shower head and your kitchen sink, and 1 gallon per minute for the other sinks. So that's all I have. That was really fast. Okay.
Thank you, Sarah. Our next speaker this afternoon is Dave Olson with Water System Services. And gosh, Dave, you've been working in this county on water systems for a long time, haven't you?
Over 25 years.
Over 25 years. I think he was involved in the very first coordinated water system plan that I was involved in. So I've known Dave for quite a while, and we've been really lucky to have somebody with his skills and ability to work with many of the small water systems that he's going to talk a little bit about some of the challenges they have and the gaps. So thanks, Dave.
Thank you. So it's a real honor and very humbling to be here with all of these well-informed professionals. It's really a treat. I'm the co-founder of Water System Services, which is a satellite management agency approved by the Department of Health for Whatcom County to operate and manage public water systems. And so that'll be more the emphasis today that you're going to see, and I think you'll find it's a lot of times where the rubber meets the road when they go for a building permit and they're not in a area where a permit exempt well may have been in the past. available, and so it's where it gets involved with the public water systems. Get tuned up here. So as mentioned earlier, there's about 415 water systems in Whatcom County, and just think for a minute, we're talking about 415 governing bodies. Just try and get two working together. We've talked earlier, I mentioned there's two different basic types of systems, Group A's and Group B's. In this slide, all I really want you to identify here is that we have the Group B systems, which are very small plats of land that were specific. And of those 415, there's 234, most of them using exempt wells, most of them unlikely to contribute to the future water supply needs of Whatcom County based on their design. Also, if you look in the middle section of the Group A systems, we have non-community systems. Most of you would identify those as corner stores, corner gas stations, small rural businesses. And again, you can see the small percentage of population that are served by those. Those are primarily permit exempt well sources. And again, these systems are not likely to contribute to the future water supply needs of Whatcom County. So that leaves us with our Group A community systems, and here you can see in the blue what I'm going to use is the government. I'm not going to say municipal because that has a lot of terms that conflict with each other when we talk about municipal water law and water rights. So these are the government systems, towns. The light blue would be those which are non-government systems, and generally rural Whatcom County, as you can see there. So the Department of Health uses an operating permit status that's color-coded, and the takeaway from this is that the green and the yellow systems are generally adequate in meeting all the Department of Health requirements. Those that are in blue are those that are adequate to serve their existing customers, but they may have some deficiencies in planning or in engineering documentation in order to be able to add new systems. The three just highlighted in yellow there, those are related to systems with nitrate contaminated sources, and they are generally under a compliance order or a compliance agreement, that they're going to be working on those issues. And today there's only one left in that yellow. Here you have the overview of the water quality issues in Whatcom County. The brown ones on the lower left there, those are generally naturally occurring arsenic in the water supply. Those systems generally address their concerns through treatment or blending of their water. On the top, you can see the blue, which are your nitrate contaminated sources. If generally speaking, that below the large block at the top, most of those systems are below the maximum contaminant level on a general basis, and they do increased sampling in order to monitor those nitrate levels. The ones around that large block at the top, those are the ones that consistently exceed the maximum contaminant level and are facing the challenge. In many cases, those small ones deliver bottled water on a regular basis to their customers for drinking and consumption and cooking. The big blue one at the top is the one that's still looking for options for supply, and earlier when Dan spoke, this is one that they're looking at that they may be able to have an outside source of supply contribute to that. The takeaway from that big blue one there is that the majority of the water that system serves is for agricultural stock watering, dairy farms. Here, and you've seen this map in a different form today, the green colors, those that have adequate water rights to serve their existing and future build-out demands in most cases. Those in yellow generally have enough for today, but not enough for the development of their systems. The ones in and the ones in red, there's actually 6 on the map, but the 3 big ones there, they are generally exceeding their water rights on an ongoing basis. However, the smaller of those 3 is actually yellow today for a variety of reasons. And the takeaway from those, all of those 3 systems primarily use their water for agricultural stock watering from those sources. If you didn't have the agricultural stock watering for those, which is a key part of our industry in Whatcom County, they would have adequate water rights for their residential domestic needs. And here is one of the big takeaways where the rubber meets the road for a lot of the residents of Whatcom County. Where can I get water if I need it? Again, we have most of the dark blue are your government systems. The light blue in the background are those non-government systems with less than 80 connections. The vast majority of those do not have any connections available for serving water to new customers. The three remaining colors, the orange, the green, and the yellow, are systems that are approved for anywhere from 80 to 1,300 connections in your rural Whatcom County. The orange ones are those that have no connections available. The yellow ones have less than 30 connections available. That leaves you with the small number of green systems. I believe there's a total of 12 to 14 out there that actually have water connections available. So today, assuming there was a pipe a reasonable distance away, that they could get a short-term, a fairly quick response and supply of water. So here is just a quick overview of the challenges these systems face. We've got water quality, water quantity, increasing and complex regulations, lack of volunteers and operator attrition, which is unique to these small systems that generally don't have staff. And we have aging infrastructure, which we've heard about earlier. And then just a brief comment about these bottom two. It's important to understand that most of these systems fall into one of two categories. Either a developer who wanted to do a significant number of homes did a system structure whereby they would put in just what's necessary for those homes, the source of water, the water rights that they applied for, and they were very specific. Or the other category is the rural farm community where they would get them together and get water from point A to point B in a very stem and branch system. And they would start with a 6-inch pipe, 4-inch pipe, 2-inch pipe to the last person. And again, they were generally designed for that initial group of people came together. The takeaway from that is the infrastructure and the design was never intended, put that thing away. Yeah, I did see it. Was never intended for the planning efforts that we're required to do today to serve future demand in the area. And so I'm just pointing out briefly, these are the 1974 documents that were in place for most of these systems when they were developing. And you can see the first one, each of these is about 20 to 30 double-sided pages. These are half-page booklets. And the guide for small system approval, the regulations for public water systems, and the overview of the Safe Drinking Water Act. Maybe 60 or 70 pages. Today there are thousands and thousands and thousands of pages that encompass that information. So just as we wrap up here today, I wanted to highlight a success story in North Whatcom County. And here you have, initially at the time, the red in the middle. They didn't have adequate water rights. The takeaway here is that they had a rural community. Most of their water was used for agricultural stock watering. A feasibility study funded by the Department of Health to work on addressing the nitrate challenge, which is the orange systems here. This feasibility study was to look at potential solutions, and that project was facilitated and managed by Whatcom PUD. And during that process, one of the things that was identified is that Sumas had some available water supply, actually in the form of water rights. And so ultimately agreement came to place where Meadowbrook was able to address their water rights issues. That allowed them to consolidate the adjacent systems to provide a different supply for them. And one of the takeaways for that is one of the sources that was no longer being able to use there is now being used for stream augmentation. So you can see how all of the pieces are coming together here. And then if we look, I just jumped ahead there, but the Hampton and the Everson were a different color. As a result of all this, there's the potential for other small systems to consolidate together here. And so in the region, you can see the green targets or the red targets. You can see how the network is much stronger as a community. These are interties, either active or emergency interties that are in place out there. And so in closing, I just wanted to highlight a technical support pilot program that's going on in Whatcom County. It's been going on for about 18 months now. And here, based on the track record of being able to assist small systems, the PUD was asked to partner with the Office of Drinking Water to develop a technical support program for our small systems and to improve their capacity. And the key here is for them to run as independent utilities to deliver safe, reliable drinking water into the future. And so some of the things we're going to be able to understand: basic local capacity needs, capacity development strategies, build relationships in the community. And one of the unique things about this is that traditionally you have statewide and national organizations that try and provide this support. And this was an effort to go ahead and get local support, building on local relationships, using local expertise to assist these small systems with knowledge, tools, and resources that are based on local information. And so just a quick report card. We've engaged with over 50% of those Group A systems that you saw that were in light blue in one of the previous maps. We've had training workshops with relevant topics for those systems. We've developed a website support. Recently, we just finished a survey of these systems that identifying where they were able to identify their needs, and they were also able to identify their concerns in order to help us guide them in the future. And then we were able to provide individual one-on-one technical assistance for the areas you see down here. And so my last slide. Ultimately, we come back to bridging the gap where the rubber meets the road for potable water systems on how do we address the gap between potable supply and demand. And so it's important that we recognize existing system limitations that I alluded to earlier. We need to encourage the capacity development. We have to continue the technical support programs that we're starting to work with now. We need to better understand the water supply challenges. This is really key. We need to reconcile the water availability that we have with land use projections, and that's important. As we heard earlier, I believe it was Doug that said, this is what we have to work with. And when you look at some of those maps where there is water available or connections available and where there isn't, that's where some of the areas we have to recognize and work within that. We need to foster dialogue among systems and with local governments. And finally, as you saw in that example we gave in North Whatcom County, we need to strengthen the regional supply through interties and consolidation.
Thank you, Dave. Our final speaker for this session is Greg Eby. He wears actually a number of hats. He not only is owner and manager of a 1,000-acre seed potato farm, he serves on the board as a board member for both the Burton and Drayton Watershed Improvement Districts, and he's a co-founder of one of our local engineering firms that some of you may have worked with, Reichard and Eby, so you're probably pretty busy. And he's going to be talking about conservation practices for agriculture.
Thank you, Sue. Before I speak about water efficiency in agriculture, I'll give you just a real brief history about my background. About 10 years ago, I retired from engineering, hung up my pocket protector back to the family farm that was established in 1919 by my grandfather. We're a seed potato operation, and all our seed potatoes start in our tissue culture lab, where they're then moved to our greenhouse, where hydroponically we grow these mini tubers, small potatoes, where we then raise 3 generations in the field to multiply the seed stocks up that we then sell them to commercial potato growers in the western United States and western Canada. Simple, right? Oops, too fast again. We grow all specialty potatoes, various colors, shapes, sizes, textures, flavors, enhanced or additional nutritional benefits over conventional russet potatoes that you might find in eastern Washington or Idaho for processing. As a high-valued crop, irrigation is very important to us. And I'm now going to talk about irrigation efficiency, which is defined by water that is beneficially used by the plant or the crop divided by water delivered to the field. So if we delivered 2 gallons of water to the field, the plant's only used 1 gallon. That would be an efficiency rate of 50%. That other gallon was lost in various ways, either in drift, evaporation, possibly excessive irrigation where it percolated down in the soil below the root system. I'd now like to talk about a few different methods of irrigation and their respective efficiencies. Probably the most common in North America is the pivot. You've probably flown over these circles in eastern Washington or the Midwest. These aren't used in our area mainly because of the small scale of agriculture. Predominantly, in the past, we've used hand lines with a pretty good efficiency rating of 70%. Very extensive labor required. You have to pick those pipes up and carry them. My father referred to that as character building. Growing up, I called it forced child labor. So we moved on to big gun technology. Tremendous labor savings. That's the hose reel there. One person can change this in about less than an hour. One of those reels can cover about 50 acres in a week. So just a tremendous labor savings, but you can see we took a big step backwards on efficiency, down to 60%. And this is primarily due, the water's pumped at a high rate of pressure out, projecting out, and there's drift, evaporation, just not a very precise form of irrigation. Drip, however, is extremely efficient, 95%, and this shows one of our potato fields under drip irrigation. This is mainly attributed to the water, and I think I handed out visual aids, right? You have little pieces of drip tape. Those tubes go alongside the plant, and the water's just distributed, flows out of that little blue line, the emitters, right into the root zone. So it's not subjected to being applied overhead to drift, evaporation, and much less evapotranspiration because it's covered in soil, covered in the plant canopy. One of the disadvantages, there's a lot of setup involved with drip irrigation. What we're trying to accomplish with all of these different systems is achieving an optimal soil moisture that the plant doesn't stress, and that's depicted here in the red line. The y-axis is the soil moisture, the x is actually over time. We can impact irrigation efficiency also on how we manage the system. We use these types of tools to monitor the soil moisture over time, and that squiggly line that looks like an EKG is the soil moisture at different times. The peaks are when water was applied, it then is reduced as the plant uptakes it. But this is showing a pretty good job of effectively holding that optimum moisture. Here's an example of a poorly managed system. A lot of water was applied, excess, that can then percolate below the root zone, not being used, wasted, also bringing nutrients down into the groundwater. Also, plants are an aerobic organism. They require oxygen. When you apply too much water, the ground's saturated and there's no oxygen in the soil that can cause stress. Conversely, at the bottom of the blue line, the little valleys, that shows when there's not enough moisture for the plants to extract moisture from the soil. It's held so tightly that the plant stresses, wilts. In the case of potatoes, the potato begins to mine its own root system, making it much less drought tolerant, and also will abort the tubers or little potatoes and dramatically reducing the yield. So my last slide, why doesn't everyone use drip? And many people do. The permanent crops or multi-annual crops such as blueberries, raspberries, even strawberries, orchards use some form of drip tape for micro irrigation. The challenge becomes with the seasonal crops. You've got to put this system in and take it out annually, and the cost can be significant. There's the cost of the labor, but also the materials involved. This can be several $100s, and if you're looking at a low-value crop such as silage corn, dairy forage, those crops maybe only have a value of $600 or $700 an acre, and this cost maybe $500, so it's not economical. It can be very economical for seed potatoes. However, the technology is still evolving. We water for about 8 weeks, so to get this system in place, get it operating, take it out, Right now, we recycle the tape. We're working to reuse that tape, but that technology's still evolving. So there is some challenges, but the advantages are tremendous. You know, the great efficiency. We're using less water, more water in the aquifer, in the streams. Great for the environment. Better crop yields. We don't get the canopy wet, which saves some disease pressure, fungal. Once you're set up, the labor can be less with automation. One disincentive we have, though, is relinquishment. State law says if you don't use your water right, or all of your water right, for a 5-year period, you could lose that. So we've gained this efficiency, not used all of our water. It could be taken away from us. So this is a huge disincentive, even a penalty for becoming more efficient. This is just one of the many challenges we face in agriculture, but I think it was Doug that said earlier, challenges also bring about opportunities. So it drives technology. There's some exciting things happening in agriculture, just even beyond drip irrigation. You know, you've probably heard of tractors that drive themselves, machines that sort the green berries out of the blue, drones that monitor and diagnose our crop health. It's pretty exciting. I'm excited to get up in the morning and go to the farm. But probably even more exciting than that is it's forced us to withdraw from our shells and collaborate with others. For a number of years, you know, commiserating amongst ourselves in coffee shops and bars wasn't working, believe it or not. So recently, we've formed these WIDs with the help of the PUD was instrumental in helping us with that. We now work on a daily basis with the Department of Ecology on some great projects with Doug and Casey. Chuck talked about one, Streamflow Augmentation. Dan talked about another in the Drayton WID, where we're looking at deep aquifers. But we're continually working to preserve, enhance, restore stream flows, habitat. Some really exciting things are being done at the WID level. We're also working with the Lummi Nation. You've probably heard of the Portage Bay partnership. We're working on water quality together with the tribe, and we look forward in strengthening that relationship. And as a large water user and a holder of land and habitat, we want to do our part in the restoration of salmon and preserving tribes' treaty rights. We're also working with resources. You all met Eric earlier. Eric is a wealth of information on this very topic. He did a lot of this in the electrical utility, and we meet regularly with him. So some really great things to be optimistic about. I'm an optimistic person anyhow, but some pretty exciting things. So we're looking forward to moving ahead in the process. Thank you very much.
Unless somebody else raises their hand. Sarah, I do actually have a question for you, because we have heard a lot of interest in rainwater catchment as an option for the people that are in a bind around the Hearst decision right now. So when you showed your slide, I may have caught it wrong, but it looked like you had to have a pretty large roof size, over 16,000 square feet, which most people, I don't know anybody with that big of a roof. Can you have more storage and a smaller roof? Or are those numbers that you provided pretty fixed?
Those, as far as I know, those numbers are pretty fixed, but you can also use like your garage, as long as you have a structure that can be used, so you can't just build a roof. But if you have a shop or something like that, that adds up pretty quick too. Because, I mean, it took me a minute, but like roofs are like this. They're not like this, obviously. Right. So it adds up pretty quick. And there can be some, we can work with people if it's a struggle, but as far as I know, those numbers are the numbers.
Okay, all right. Questions? All right, we've got a question here.
I understand that you have to have special roof coverings in order to catch water for a potable system. What if it's not for potable purposes? Could you have a roof with asphalt shingles and save it for, lawn watering, whatever, ever?
You could. So for the health department, our main mission is public health. So we want to make sure people have a drinking water source that's safe. Right. But if you already have a house and you want to put in a rainwater catchment system to water your roses, you can go ahead and do that.
Very good, thank you.
I'll add another little source of information for that question onto that. Department of Ecology has actually done quite a bit of research and testing on different water quality from different roof types in our state. So you might go to their website to take a look, because we actually got better news than what we thought in terms of being able to say that some of the roofs we thought might be bigger problems were not quite what we thought. And there's a lot of applications and reasons why folks might want to use rainwater catchment for particularly outside irrigation, because right now most of the time you're using treated water for that, and that seems like kind of a waste. So, other questions?
Sarah, you mentioned that Whatcom County chose not to implement the gray water regulations for irrigation. Can you share why?
Money. Lack of money. Resources.
Hi. I heard the red zone we saw in some pictures. Now I don't remember whose it was, but the nitrates were high in those zones, and so I'm wondering, one, if you can tell us, is the source of that from agriculture, I'm guessing, or I'm wondering what the source is on that. And then I'm also wondering if you talked about using that water for the stream restoration, and so if it is high in nitrates, would that be harmful for streams at all?
Well, I'm going to probably redirect you to somebody else in the room that is much more qualified to answer that question. But in general, on the first question, some of it has to do with past practices, and we've talked about the nitrate, the cross-border nitrate management programs that they've worked on, and you've also heard that in some reports the nitrate levels are actually trending down. So they're in part to past agricultural practices, many of which have improved. There are certainly some impacts from the cross-border agricultural practices too. So it's a broad basin. Beyond that, I couldn't address that specifically. Your second question was?
Streamflow augmentation.
Oh, streamflow augmentation. And so actually with the nitrate levels on one of the wells that was used, it was very marginal, but it was above the maximum contaminant level, so it had to be addressed from that standpoint. And so that's one of the things that we looked in, and we worked with actually Department of Fisheries. And our bigger concern actually with the Department of Fisheries and those that were involved in that was actually dissolved oxygen, not having enough. So groundwater typically is not going to have that. So they didn't feel that the nitrate contamination, which was already naturally occurring in the groundwater, was a concern. And the primary concern was having enough dissolved oxygen. And so when the stream augmentation went in for that particular project, they simply were able to aerate that, add oxygen running over various rocks and falls in a very simple method. So that's the best that I can answer that one.
And I was actually looking around for Doug Allen, and Henry handed him the mic. So, Doug, you can actually add a little more information into the nitrate source question and some of the more recent work that's just gotten started.
Right. So the starting way back, early 1990s, we had a cross-boundary work group on nitrates, and I think everybody would agree that some amount of that, some of the nitrates that comes across the border and could affect groundwater in the Sumas area probably came from the Canadian side. But then there are many other wells that have high nitrates that are south and west of that there could be some effect, but that's a long way for it to go. So most of that is probably coming from the U.S. side. So it's on both sides of the border. It's not all from agriculture. So there are multiple sources, and we could get into talking about, well, is it from berries or from livestock, and that's really not real helpful at this point. Everybody needs to do everything they can to reduce the amount of nitrogen that gets into our groundwater. The Abbotsford Sumas Aquifer is shallow and very susceptible to contamination. So we think we're making progress, and time will tell.
And I'll add a little bit of additional information onto that. Doug's right. Way back in the 90s, we did have what was called the Linden Everson Nooksack Sumas study. Some people, including Craig McConnell, were actually involved in that. And we looked very closely at the different sources at that time. Yes, there were lots of different sources. Agriculture was named as one of them. It precipitated a lot of cross-border work and discussions that also did sort of fizzle out over time. And again, I want to just reiterate that some of the new efforts that are going on across border are going to be looking once again at some of the sources and solutions that are out there. So it's an ongoing just topic that we're aware of, that we're trying to deal with. So other questions? Up there.
Hey, not really a question, but I wanted to add to what Greg was saying about water use efficiency in ag, because it seems to be such a large percentage of what we use. And I wanted to double down on what Eric said earlier about the need for the state and other entities to do more research and figure out some ways to assist farmers in the water use efficiency. Drip irrigation is suitable for some crops, but I don't want to see farmers in general demonized for using overhead watering or other methods. There are new technologies like smartphone apps that allow farmers to sort of fine-tune the amount of water they're using, according to how much rainfall. And of course, there's the problem of plastic, increasing use of plastic in our agricultural fields. So just want everyone's minds to stay open to alternatives to drip irrigation and working together to find more water use efficiencies for farmers.
Great, thank you. Any more questions? Last call for questions? Okay, great.